Hi everyone and welcome to this video. Last time we have introduced the field of artificial life and we have studied a system of particles which follow Newton-like rules. So in this video we are going to continue with this topic, artificial life, and we are going to continue to study systems of particles, more or less like what we have done in the previous video. But what we will introduce here is a set of more realistic rules. And as an interesting result of this is that you will see that practically we can observe more realistic, more lifelike or more complex phenomena emerging in this system of particles. Of course, everything will be done in QBasic, so if you are interested, you can go to this link and download the interpreter, actually the compiler, so that you can duplicate all the results that you will see. And of course, I will present also a lot of examples so that you can actually understand very clearly what is this artificial life and why more realistic rules bring the emergence of more complex phenomena. As usual, I'm reporting here an article. This is an article coming from Wikipedia, so if you are interested, you can dig into more details. This is definitely a good starting point if you want to know more. And as always, I want to thank you all for being here today and for continuing to support this channel. So last time I have used the figure that you see on the screen here to explain what kind of particles we are going to study. And in practice, this is an ensemble of two-dimensional particles which have certain mathematical features. So first of all, they have a position and a velocity which consist of two components since we are in a two-dimensional space, but they also have a color. And the color is practically what is going to dictate if a force is repulsive or if it is an attractive force. So from this point of view, nothing has changed. This is exactly the same system that we did study in the previous video. I will now go ahead with the rules that are applied. These are more realistic, more sophisticated, which is what makes a difference when you run the program. To explain these rules, I'm using the figure that you see here on the screen. And the left-hand side of this figure is essentially the set of rules that we have used in the previous video, which were Newtonian-like rules, but not exactly Newton physics. For example, one thing that changes here is when you define the force or when you compute the force is inversely proportional to the distance, but not to the square of the distance. On the right hand side of the figure, you see a set of more realistic rules. These are the rules that we are going to use. So the dependence over the distance is going to be very different now, but still it doesn't depend on d square. So these are more realistic and yet they are not exactly Newtonian physics. So we still have a concept of distance, and if you see, this is exactly the same concept that we had previously. So we have essentially two particles and we can define the distance between these two particles. But then when we compute the force, this is where things change drastically. First of all, as you can see now, we have three components of forces which depends on the distance. So depending on what is the value of this distance, we are going to use a different term for the force. And what I'm showing here, this is the x component of the force for the nth particle. Of course, we would need also a y component of the force, but this is very simple to understand. I mean, you can generalize, you can get Fy from Fx in the very same way. So again, fx and fy, they are sums of many terms, but these terms now can be different. But still, what we have here is sums of terms, because every particle is essentially interacting with every other particle of the ensemble. Of course, in these sums, we don't take into account the particle interacting with each other, which would be a non-physical effect that we would have in the simulation. For the velocity, nothing changes. Once you have computed the speed, once you have computed the force, you know how to compute the velocity. One thing that also we are going to try here is that G and L, so G is a matrix, and all these terms are practically numbers ranging between -1 and +1, but this time we are going to make things slightly more sophisticated. So we will start from completely random matrices G, but also we will use a symmetric matrices G and see what is the difference that is coming in the simulations. What is the difference that is appearing in the simulations that we perform. So we are now ready to go through the code that I have prepared to explain how to simulate these systems. The very first thing we are going to do is to go through the list so that you can stop this video in any moment and then go through the details. After the listing, I'm going to explain some parts of this code. So the initial part of this program is practically the same as in the previous video. What we are trying to do here is to create a full screen on which we want to plot the results. And what is very important at the beginning of this program is the seed here, because this is going to have a drastic influence on the results that you are going to see. So every example that I'm going to show at the end of this video, I will report the seed. So if you change the seed accordingly, you will be able to duplicate the results that I have selected. So if we now go ahead, this is more or less the same things that we have seen in the previous video. So we are practically defining a maximum number of particles allowed, and we define an index for every color. So the index 1 would correspond to the color red, the index 2 would correspond to the color green, and so on and so on. And here we define exactly the same global variables that we have seen in the previous video. So NT is going to be the total number of time steps during the simulation, NP is going to be the total number of particles during the simulation, NX and NY are going to be practically the dimensions of the grid that we use to plot the particles. And then we have a few more variables which have a meaning that we are going to see while we browse through the other parts of the code. So in this particular case here we have NT equal 4000, so we will have 4000 time steps for every simulation, and NP is equal to 1024, so this will be the total number of particles that we are going to simulate during a run. These represent the resolution of the grid on which we want to plot the grids. And finally here what you see is we have a bunch of time variables that we need to define. Since we are now introducing a more realistic set of evolution rules, we need the concept of time. So we will set a final time and we will define a delta t, or time step dt, which is practically equal to the final time divided by the number of time steps that we want to have during the simulation. Similarly, we are going to define another global variable, which is the half-life for friction mechanism. So we are introducing now a friction mechanism during the simulation, and this is practically specified through this value here. And then what is interesting also, especially if you want to duplicate the results that I'm going to show, is this S flag here, which practically says if you want to have a G to be symmetric or completely random. So if it is equal to 0, this is going to be a random matrix, but if it is set to 1, this would be a random matrix that has a symmetric structure. Then we also define other values. This is a beta that we are going to use once we want to select what is the term for the force that we need to compute. What you see here, these are the usual global arrays that we need in order to define the ensemble of particles. This has been explained in the previous video, and nothing has changed since then. In the very same way, we define now, we reset a few let's say arrays, and this is done in exactly the same way we were doing previously. Nothing has changed from this perspective. So G, for example, is going to be a matrix which elements range between -1 and +1, and they can be practically random. In the same way, we define radius, which is going to be a value between 1 and 150. And then if the symmetry flag is equal to 1, then what we do is that we assign Gij equal to Gji. The same happens for the radius, so in practice we are making the matrix symmetric. Then we start from, we can now apply the initial conditions. These are completely the same as in the previous video. So in practice you define an initial position for every particle, and these positions are practically going to be random. The velocity for every particle, the initial velocity, is going to be equal to 0. The color is going to be random. And then if we go ahead, now we are entering essentially the main loop for the time steps. So the index I is going to range between 1 and nt, and this will be practically the index representing the time step. And then here, for example, we update the friction mechanism that is in this particular case a constant, but this constant is going to be time dependent. So this becomes at least one level more complex than what we were doing before. Then in the same way we did previously, we are going to evolve every particle. So now we have an index here, index n, that ranges from 1 to np, where np is the total number of particles. And then in this for loop here, what we are going to do is we are going to define the concept of distance between two particles, and then define the force that you see here. And the force, as you can see now, this is different from what we had in the previous code, because we now have 3 different components for the force. So we have, or let's say 3 different terms to define the force. So this is the first term, when the distance is smaller or equal to than the value beta. Then here we have a second term in case d is bigger than beta but still is smaller than the radius. And if we are in a completely different situation, f, now this is the third option, the third term, f is equal to 0. But then, as you can see, we update the 2 components of the force in the same way we did before. and we update the velocity of the particle, but as you can see, this is different from what we were doing before. This is different in two ways. The first way is that now here we have a mu coefficient that is practically going to change with time, so this is going to have an effect on the update of the velocity. And then also, when we are updating the velocity, we multiply the force times dt. So practically this update term here is going to depend on the value dt that was defined at the beginning. And then, as you can see here, the same happened for the position. Once we want to update the position, now things are slightly different and more realistic, because now the velocity is multiplied by the time. So in practice, what we are doing here, we are giving let's say more complexity to the rules that we are using. And if you want to compare to Newtonian physics, what you will see is that this is closer to Newtonian physics, but yet it is not Newtonian, exactly Newtonian physics. So now here what we have in this part of the code is what we had before. So in practice, we want to apply reflective boundary conditions. We want to make sure that no particles go out of the spatial domain, and we impose conditions when this is the case. So we re-update the position and the velocity depending on what just happened to the particle. And then, of course, we create the grid that we are going to plot, and we plot the grid. So this routine here is exactly the same as before. So what we are doing is that we define a grid which initially has every cell equal to 0, but then we check where a particle is staying in the grid, and we assign a value to the cell of the grid which is exactly representing the color of the particle that is staying in that particular cell of the grid. Once we have the grid, we can plot it. This is done exactly in the same way as in the previous video. So we practically reset the screen initially, and then we go through every cell of the grid, and we change the color of the cell depending on what color the particle that is in that cell has. This complete in practice the explanation of this code. I am going to show several examples now in the final part of this video. As always, I want to thank you all for being here today, for your attention, and I hope to see you in the next one.